Hi.
Hey Jack, how are you?
Okay, how are you?
Good. Friday again.
Friday again. So as you had asked me to kind of post up a template on that AI fabrics, and Jay's gonna add his stuff. We can ping Prakash. And
Sure.
and as we had with the conversation with Hesham, we're recording now, but the conversation with Hesham, um, I started a framework. Here's what we plan to do for the neuromorphic kind of thing. So hopefully that's good enough that they can start editing, now that we have a document and what would we commit to, how would some things work, go from there. Okay.
Yeah, sounds great. Yeah, I think it's a great idea to start with something. Otherwise, so we are just talking without any action.
Yep.
So this way we have a starting point. It's great.
Yep. So yeah, so we can start with the talk today. I put the status up in the presentation directory, and I'll update it. I have a couple of conversations next week, but I'll update it and we'll go from there. So we can do our talk and sounds good for a Friday. How's that sound?
Sure. Oh, do you mean like you update first and then we start a talk, or we start a talk first and then followed by your updates?
I think we can start with the talk and see
Okay.
where it goes and allocate as much time as we need. And if we need to do a quick update, otherwise it's on the share drive. All the bullets, exactly where everything is, all the things, the docs, things like that. And to your point, we'll just keep using the share drive and the
Mm-hmm.
and the wiki and chip away, so that way everybody we can do things async because not everybody can make it. So, but it's up, and if we have time in the end, I'll throw it up and we can kind of just do a quick thing. But if we kind of use the whole hour, then we use the whole hour. That sounds good to me.
Okay. Sounds good.
Yeah.
I see Professor Leeds is already online. Hello, Professor.
Hello, how are you?
Good.
Thanks for having me.
Yeah, we are honored to have you to give a talk to the community here.
Yeah, thanks. Should I already set up? Yeah,
Yeah, you can set it up, but in the meantime, we can wait a couple more minutes for people to
sure.
join.
Yeah, because there's a composable memory group meeting that goes right before this, and it was definitely going to go long. So,
hmm
and so they meet during the lunchtime on the East Coast. And so they're right before us, and sometimes it runs over. So we typically start about 5 after, if that helps.
Yeah, that's totally fine. Oh, where did my title go? There it is.
Yes. This is a perfect topic too. So yeah, hopefully Brian will join as well. So we have a couple of people from the other space going through. So and as we're getting started, Hesham, were you able to get to that document in the WIP directory? I guess
Yes,
he's
I got it. I got it. But we need to discuss after Professor Hens' presentation. What do you
okay.
plan to do for neuromorphic computing?
Well, so I started a proposal and it has work items, for a work stream, and so we can edit that document however you think we should, you know.
Excellent. But from logistics point of view, uh, the work stream need to be is approved, or there is something that need to be done to approve it. I don't know the process.
Yeah. So right, I'll be brutally honest. The way it gets approved, I think, and because Weifeng and we had talked, we have two. We have the fabric ones we're doing much more on the training side. We started the algorithms one because Yasa and team are willing to put effort in and have funding and students and things like that. And we're working towards a common goal. So if people are willing to work on it, agree to the work items and produce and collaborate and do things like that, I think that's great. To start a work stream and say, hey, I want this work stream approved, and then nobody wants to work on it, that would be difficult.
Exactly. So the first step after your document is to get the ball rolling and get people to work on it and interested to
Yes.
invest the time. to do the required work, right? This
Yep.
is the process, right? Okay, okay.
So I think as a collective, the documents up there, we'll edit it.
Yeah,
Well, as we go through, we don't want to take months to edit. So if by the next meeting, if we have all the edits in, then we can discuss it as a topic in the next meeting. Wei Feng and I can, as we kind of lead through the team, and if people are willing to sign up and that's what we're comfortable with and everybody's kind of gone through, then we can have that discussion and decide how we want to move it forward.
excellent. And by the way, did you attend this IBM?
Yes, I did.
Excellent, because we got 63 people interested in this.
Oh, yeah. And there's,
Yeah, huge number of interest.
yep. And
I was surprised.
yeah, so we'll kind of I will close out this conversation as we kind of shift over, but they also, I think, beginning of this week, somebody just published kind of a market analysis projection, things like this for the next
Yes, yes, got it.
decade where they see neuromorphic computing going. And so I'm going to speak to Yasa about algorithms and mapping and doing things like that. So
Excellent. And
so
by the way, Professor Hens, and I am very happy that he is going to present because I met him at the CMBS Summit and he made excellent presentation. He also knows Professor Jason, who is in spiking neural networks, neuromorphic computing in the same university.
okay,
So I hope Professor Heiner will also be supportive to what we are doing.
sure. All
Okay,
right, so
I
close
think
out this
now
conversation.
it's
Yep, go ahead.
time. It's 6 past hour already,
Okay.
so maybe we can start a
Sure,
talk from
sure.
Professor Leeds. Go ahead, Professor Leeds, give a short introduction about yourself, and then you can start your presentation. Thank you.
Okay, great. So thanks, Hisham and Wei Feng, for inviting me, having me here. It's a pleasure. So I'm an associate professor at UC Santa Cruz, just across the hill. I am the Kumar Valavali Endowed Chair for Storage Systems, and I also directing the Center for Research in Storage Systems, CRSS, which is a industry academia collaboration to perform impactful research in storage systems, data center systems, systems for AI, and more. We had released some highly impactful projects. So, for instance, Ceph, which you may know, came out of our group. And right now it's a group of about 3, 4 faculty, 15 students. I'll give you another brief overview of the lab later. So personally, one of my key research focuses is optimizing across the hardware software interface, right? So doing hardware software co-design, including computer architecture, chip design, compiler infrastructure, operating systems, and applications. So one reason why we think this needs to be done going forward is because we're seeing that we are running into scaling issues such as Moore's law is slowing down, memory capacity is not increasing as it did in the past, and so we can no longer afford to innovate and work on these abstracted, decoupled layers, hardware, system software applications. Individually, we have to leverage hardware software co-design, cross-layer optimizations to continue driving performance and efficiency gains. And so one talk I want to give today is about how we can use software hints to improve substantially the performance and efficiency of CXL SSDs. Those are hybrid devices connected to CXL to the host system, consisting of different types of memory tiers, memory, flash, PMEM possibly as well. And so I'm going to talk about how these new type of devices can be made more efficient with hardware-software co-design. And I hope that's a good topic for this audience. All right, let me dive in. So why are we doing this? Why are we even looking at these new type of devices? If you check out this graph over here, which shows DRAM capacity scaling over the last 70 years, then note the log scale on the y-axis on the left. You will see a nice linear improvement translating in roughly a doubling of memory capacity every 3 years or so. But then when you're looking at the end, you're seeing that this is considerably slowing down. We're still seeing improvements in terms of price per bit, but it has now slowed down to a 2x per decade. That's a problem, in particular as applications and also compute and networking has been scaling much faster. So we kind of are running out of memory capacity. And we can see that if you buy a server today, you're almost paying half of the money for DRAM. And even also, if you look at GPUs, right, high bandwidth memory is one of the most costly components on these type of devices. So that's about DRAM. If you look at flash here on the right, it looks a little bit more promising due to 3D stacking. We have been able to scale NAND flash much better. So here it is expected that even for the next 10 or so years, we will continue to scale much faster than we are able to do with DRAM. And if you again look at workloads, right, these are just scaling and requesting more and more memory capacity as we speak. GPT-3 was trained on 45 terabytes of data. I'm sure GPT-4 and beyond has been scaling the amount of data further quite dramatically. If you look at Netflix, Amazon, they make heavy use of deep learning recommendation models. These operate on terabytes of embeddings. And if you're looking at these upcoming retrieval augmented generation systems based on LLMs, again, we have to work with multi-terabyte vector databases. And it's not only capacity, these applications are very performance demanding, right? They want high capacity, high bandwidth, low latency, the best of everything. Okay, so how can we bridge that gap of slowing down DRAM capacity scaling and increasing demands for more faster memory? Well, we think CXL can be part of the solution. What it allows to do is to combine different types of memory and storage technologies and make them directly accessible through a byte addressable interface, completely bypassing any OS overheads that plagued us when trying this with storage, right? So there have been a lot of works on software-defined storage, computation and storage, and it has been a very slow technology to adapt, I believe mostly because it requires a whole rewrite of the software ecosystem. Byte addressable CXL makes this very easy, right? You can expose whatever memory technology you have as a just virtual range of addresses, and your applications can continue running on these devices unmodified. And then it has some other nice feature like cache coherency, open standard that allows us to innovate as researchers. Was there a question? Right. Okay, so status quo about this. We are seeing first devices emerging, but there's not a lot available. It's kind of a slow rollout. Those devices that are available of course, are closed source. They are fully owned and managed by the manufacturer. And these devices offer limited programmability. They show low performance in many scenarios. And more generally, we don't really know yet how to effectively use these devices and how to architect them in an optimal way, right? So what type of memories should we use? What type of caching? What capacities? How should the architecture of these devices look like? And also on the software side. So what maybe portions of the application can run on these devices without penalizing performance too much. And so this requires a deep design space exploration combining both hardware and software. So again, we need to optimize across these layers. Okay, so there is a need, if we want to do that with CXL, there's a need for emulating all these different scenarios. And that's where my lab went and built a CXL SSD emulator. We call it Convey. It allows to explore both the hardware and the software or application side. On the hardware, you can essentially try out the different types of memory tiers, the caching policies, how you move data between these different tiers using replacement policies and prefetching strategies. How to exactly place the data. Should this be controlled or should we allow some hints from the software? Should we leave the device itself manage this? How should the software-hardware interface look like? Do we just want the byte addressable linear address space interface, or do we need something else, for instance, to provide hints from software to hardware? And then on the application side, given we have one of these devices, right, how can we ensure that the applications run in an optimized way on these devices? So basically, how if we say we need these software hints, we need some controllability from software, how can we implement and embed this into application in the most efficient way?
So I have a quick question.
Yeah, go ahead.
As you look at this, do you separate at all kind of the problem space that you're looking at and the optimizations that are, where you see kind of the gaps and then the opportunities that we would need to solve, and then this is a specific implementation that can solve this, or will you, I guess, as you go through the slides, talk about for this particular, CXL SSD, all the different problem spaces that this particular device or implementation can address as we start to look at the data flows?
Yeah, I think we try to make it as flexible as possible to cover as many of these problem spaces. You may come up with some that we hadn't considered yet, right? That could be an interesting discussion going forward. So the idea is really given a set of representative important applications, say benchmarks, right? And a hardware architecture that we can start with, can we use this system to iteratively improve both of them, right? So essentially using the simulator to measure performance or whatever characteristics, power, etc., data movement operations you want to measure on such a system, finding out why an application doesn't perform well, and then being able to address these problems either on the software or hardware level or in a combined fashion.
Okay, thank you.
Okay, couple more information about this simulator. It's emulated in QEMU. It looks as follows. So on the top, we are able to run unmodified application, unmodified Linux binaries. We then expose the CXL device through different interfaces to software. Within the CXL device, we support a device DRAM memory region. That is the virtual address space that we basically map into user application space to access the CXL device using load stores. And then we have another separate shared memory region, which can be used to transfer hints from software to the hardware and also telemetry data up from hardware to software, right? So this is a separate interface. The nice thing with CXL is that this shared memory region can be cached in host memory. And so it basically appears to be readily accessible by user space applications, although, of course, the telemetry data is originally generated by or within the SSD. And then we emulate multiple hardware components. So down there we have, say, flash media, but it could be another type of media as well. We can implement near data processing kernels for computation acceleration. We have built a module that does smart data placement decisions. Then we have an in-device caching and prefetching unit. And because the emulator is written in software, you can add new NDP kernels, new modules as you wish, right? Okay, so we did a lot of work to first make it faster. QEMU has some basic implementation support of CXL right now. There's a number of companies that are doing great work here. And this is mostly for bring up, so to kind of develop software drivers and low-level hardware for these new upcoming CXL devices. But unfortunately, the performance is very, very low, so you cannot effectively run realistic applications on the upstream QEMU. So we did a number of changes to it, leading to a 100x higher bandwidth and 100x lower latency. So a simulation on QEMU that would have taken 100 minutes will now take 1 minute, right, with our new
Yeah, he
context.
knows not to send that. It was supposed to be.
Pardon? Hello? Okay, so I'm not going to go into too many details. If you're interested, we can talk about this offline. So we achieve this speed up mostly by introducing a user fault FD-based DRAM cache. So every address, every page that is being cached in the cache and that does not need to be served by the flash layer, that is transparently mapped into user space, and so accesses to this cache are very fast. They don't need to be simulated by the QEMU simulator because there are no flash accesses, there are no accesses to these NDP and whatever systems, and so we can do this very fast. And by doing so, we get this significant performance speed up. Now, I think most interesting for this audience here is the hardware software co-design aspect, right? So one thing we saw is that we need software hints to realize adequate performance, because if you just take these new devices, plug them in, yes, it is great that we can transparently run software without modifying it because it's byte addressable flash memory, but the performance is not adequate, and we need to do a little bit more to make this work, and this section is about that. So first question that we want to ask ourselves is, when we look at improving performance for applications running on such a CXL SSD, right? Why don't we just implement all these optimizations, say prefetching, smart replacement policy, data movement, data management engines? Why don't we just implement these in hardware? And by doing so, maybe we get great performance and we do not have to touch the software at all, right? That's the old way of thinking, where we just do implement optimizations on the hardware layer itself, which is nice because the software does not have to be changed. And it's even easier to establish such products in the market. Well, there is a number of issues that make this really hard, and which we believe require these software hardware co-design techniques. So one is that voice to physical address translation causes these nonlinear mappings, right? So let's say you have a highly predictable memory access pattern on the virtual address layer. So you have a streaming workload or maybe even a graph workload that does indirect memory accesses, or some AI workload that just does a big, well-predictable, a large matrix multiply. Then the problem is that because the virtual to physical address translation scheme that modern CPUs use, they can map these contiguous linear virtual addresses to essentially random physical addresses, destroying these predictable memory accesses. So within a page, say 4K, because pages are mapped at the granularity of pages, these patterns survive, right? Which is why CPU, cache, and prefetching mechanisms work, because they generally work within a page, but across pages, it becomes very difficult. And this is what we have to do because CXL flash devices store their data using 4K pages and beyond. If you share such a CXL device across multiple threads or processes, workloads, which you likely want to do in a data center environment where you have many different tenants working or operating on a virtualized machine, including a virtualized SSD or CXL device, then you will see interleaved, obfuscated patterns of these workloads running in parallel on such a device. And more generally, the device itself lacks application context. It just sees a stream of addresses, and it has no clue what data structures these streams generate. It doesn't really know a lot about the hotness and the locality of the data structures emitting these memory requests, and it's very difficult to relearn this on the hardware level. And why should we, if we have all this information available on the software level?
So if I listen to
Go
what you
ahead.
said, as we started with intent. So from the page that you were just on, looking at that, we can do hot and cold pages, but the pages really don't make any difference to the application. You know, I'm going to start caching pages or predicting pages, but it's not in an application context or a data access profile from a workload perspective. It's just really pages, irrespective of the application, is what you're saying.
That is correct. And there's more like this. So for instance, let's say you have two different data structures on the software level, on the application level, right? One that maybe an array kind of data structure, which is usually accessed using easy to predict sequential memory access pattern. And then you have some pointer-based data structures, trees, which are much more difficult or which perform in some cases random pointer chasing basically accesses. these two data structures may reside on the same page, and then one of these data structure may be easy and one may be hard to predict, and one may be hot and one may be cold, and you're mixing all that on the page. And how should now the hardware figure out what's going on there, right? But if we do smart hardware software co-design, then we will learn the individual hotness of these data structures, the individual predictability of these data structures. And we will then migrate or allocate these data structures in a smarter way so that, for instance, these different patterns are not going to be combined on the same page or maybe even block in a flash drive, so that we can do management of like minimize garbage collection and put data with similar hotness into the same region and things like that, right? We can do these kind of informations if we have application context.
Okay, so you'd coalesce based on the application then, and not on essentially just memory translation. Okay.
Right, and I think we're claiming this becomes much easier if you allow the software and hardware to interact, right? So there have been approaches where the hardware itself tries to kind of separate these data streams and migrate it or put them, but it's very hard, and you need a lot of metadata to learn what's happening, and then you need indirection layers to migrate the data. But if we combine telemetry data to help us determining the root cause for problems, and then allowing the software, say, allocation, right? So these things can still be encapsulated nicely, say, in malloc, right? So it doesn't really mean that the user has to do all these fine grain segmentation and partitioning of its data structures. We can possibly hide this and encapsulate this on system layer software, and thus getting like the benefits of both much more efficient execution and minimal software productivity or modification overheads.
Okay, so then I apologize for all the questions, but then if I did a malloc based on the application that I'm loading, based on if I've run it before, things like that in telemetry, now I have a profile. So when I do the malloc, now I can basically understand the profile of that application, how it load data, and I could look at kind of the access patterns that may come. It could be sequential, could be random, it could be sparse, it could be dense, and a lot of those things. And so that malloc allows me to find a profile that matches the application, but I also could find I could start to group applications that are very similar in terms of access patterns and things like that, based on your intent.
Exactly. Yeah.
Okay, so
That's
I could create intent profiles. Thank you.
And again, I want to stress this is much more important in these new types of devices, which have so very different memory latency and bandwidth characteristics, right? If you consider you're just working on flat DRAM, it almost doesn't matter, right? There is not a big incentive to spend a lot of time to optimize your memory layout. You may get by like placing your data perfectly in DRAM and like considering like what type of data structures and patterns you're using. This may give you a slight benefit, but it's probably often it hasn't been worth it. While on these CXL devices, it makes a major difference, right? To place your data in an optimal way.
Okay, but you're also looking at, from your CXL device, you talked about not only expanders, but near data processing, things like that, and also looking at new applications like RAG, which have embedding tables and sparse operations.
Yes. So one main problem, right, of these CXL flash devices is, of course, the high flash latency and also the bandwidth requirements across the PCI/CXL interface. So one obvious thing is to offload computation to do some near data processing. Again, I think with computational storage, this hasn't really worked out, because if you had some host level kernel, you wanted to run it on the computational storage device, you would have to completely rewrite it because you can no longer use malloc and all that. You have to write on, you have to work on flash pages, etc. And with CXL, it's much easier possible now. So if we see, again, using our telemetry data, hey, there is some particular process in the application that is limited by, say, CXL bandwidth, right? Then we can relatively easily, if we have some computational hardware on the storage or flash device, we can migrate that to the device, register it as an NDP kernel, and then modify the application in the way that instead of executing that kernel directly, it would have to offload it to the device and then just check when the kernel has finished. So this has become much easier to implement with CXL.
Thank you.
So here's some ideas how this can be actually done. So I already mentioned we have this shared memory region that we use both for transferring telemetry data up the stack from hardware to software, and we also use it to emit these software hints, right? So it's basically a straightforward API that we can trigger by software, either system level software like allocators, but it could also be done by the application itself. And then you have essentially a hint ID, which will then trigger a particular kernel. And this could be a hint as easy as prefetch address X from, or range X from flash into the DRAM cache, or it could be executing an NDP kernel. These hints are based on virtual addresses, so applications just say, hey, I want to move, for instance, migrate this virtual address range, and then our system ensures that the device will move the correct physical pages corresponding to these to this virtual address range. And then here's a couple more information about the approach that we implemented. So first step, telemetry database root cause analysis. You first have to figure out what is really limiting your performance, right? So you don't want to start throwing in these hints everywhere. You really want to focus on the performance relevant memory accesses, data structures, etc. We have then built a system for compiler assisted software hint injection. So for instance, we have developed an approach that extracts hard to predict prefetch patterns like indirect memory accesses that are common in graph applications where you traverse, like in a breadth first search kind of algorithm, the neighbors, and then you want to perform a task on the neighbors of the neighbors and so forth, right? It's iterative or recursive algorithm. And in that case, these prefetch patterns are very, they kind of look random on a first sight. But if you consider what the application does, then you can actually make those predictable. And we've built a system which observes these and then automatically injects software hints using a compiler pass. So we essentially run our application, we profile it, and then we recompile it by injecting these prefetch hints automatically. And so the software developer really doesn't have to do anything but click the compile button twice, right? So it's still very convenient to implement these kind of techniques.
So with the hint, do I have the ability to convey kind of memory addressing allocation, usage, things like that, profiles. If your near data processing has different kinds of processing elements to handle your data structures differently, could I also hint that would say, hey, direct to something which is much more sparse, which is much more dense, or handles matrices and tensors different than something else? Could I do it like that too?
Yeah, I think we haven't implemented all that yet. So we have a couple use cases that I'm going to show. One of my student is working and spending more time on these NDP kernels, and he's looking at questions like that, but this is still an ongoing area of work for us.
Got it. Thank you.
Kind of to Jack's question, it sounds like it's almost like if you had, like most of these traditional AI compilers, you have some multi-level IR, which you can provide hints at different levels, either the raise or lower, to help you in more efficiently do your memory accesses, according to what the workloads is. Is that the direction you're kind of exploring these things, Heiner?
Yeah, I think that's a good point, right? So these different layers exist at various stages. Even on the compiler level, you have LLVM IR, you have machine code, but you could also consider the application software, the source code that the programmer uses, as some layer where we can introduce these hints. And then you could do it on the LLVM IR layer, and you could also patch your machine code, and you could do it in hardware. So there's all these different layers where you can do it. Generally, you have a different level of information on each of these layers. The very top, you have all the application context, right? You know what type of data structure, for instance, some pointer refers to. But oftentimes, there's also information that is readily available at lower levels of the stack and not to software, right? So you may, as a programmer, know, okay, this is a easy to predict data structure, and this is a pointer chasing kind of data structure. But do you really know, without doing profiling, etc., how much time exactly is spent in each of these data structures, right? Does it really matter if you're only spending 1% of your time in this pointer chasing data structure and 99% in this other one? Then you will still be able to just ignore this essentially less efficient data structure accesses. So you need to combine, I think, high-level context knowledge with low-level profiling and performance data to get the full picture.
Yeah, I was just reading something this morning that there's someone posted on LinkedIn. It was about, and it's very specific. It's to NVIDIA and some sort of matrix transformation algorithm that they use to be able to maximize throughput and get rid of bank conflicts in memory. So, I mean, it kind of has a similar flavor. So I don't know if you're familiar with that, but that work, but I can send you a pointer, Heiner, but
Sure.
it seems like this kind of flavor of things, could be, something that you would consider.
Yeah, send me a link, and I'm happy to look at it and give you a more
Okay.
informed answer. Okay, I guess we all. Whoops, I clicked on one of the links, I guess, in the chat. Let me go through the rest of the presentation real quick so that we have a little bit more time. So right now we are looking at 3 case studies: prefetching, data lifetime optimization, and memory layout optimization. And these utilize this approach of profiling, exploring telemetry data, and then injecting these software hints into applications. So using our QEMU Convey simulator, then unmodified Linux binaries, yes, we will inject these hints so they do not stay perfectly unmodified, but it's a really small amount of work that you have to do to support these hints. And then for now, we have been looking at vector embedding search for like RAG systems and also some of these graph applications. And then because our simulator is much faster than what upstream QEMU can support, we can really run these scenarios applications on realistic data sets. There's still some slowdown, right? It's not native performance, but it's pretty good. And so this is our first use case study on prefetching, where we see how can we use these software hints to migrate data from low latency flash into the CXL DRAM cache using software hints, so that when the demand access, the byte addressable access, is received by the CXL device, that can be served as much as possible from the DRAM cache, avoiding the high flash latency. And this has really a significant impact on performance. And we try here different techniques, different prefetch distances on where we inject these prefetches to obtain timely prefetches. And then we observe like by how much the on-demand number of flash accesses is reduced, right? By hitting more often in the DRAM cache. And we see that this works sometimes better and sometimes less good, depending on these applications, right? So there is some where we can drop these flash accesses substantially, and then some others where we see with a large prefetch distance, at least we almost see no gains. So again, it's application, it's data structure specific. Some applications may never work on these kind of architectures, but some of them we can make work if we exploit these software hardware optimizations. We also looked at data lifetime hints. That's essentially profiling the locality. How much can a particular memory access or stream benefit from caching? Because there's a lot of temporal and spatial reuse, and then prioritize these objects to be stored in the cache. And so again, we see for all these 4 applications substantial benefits, the order of 70% reduction in flash accesses if we ensure that the right data is cached, and some data that doesn't benefit from caches, we can afford retrieving that from flash. And then the last is memory layout. So here we again found that these different data structures work. So in many of these applications, you can essentially decide whether you want to use an array of structs or structs of an array. And so by transforming software data structures, we found again that we can enable significant performance optimizations. So what we did here again was telemetry data profiling to determine when data was inefficiently accessed from these pages, because essentially data that should not belong to each other was stored on a 4K page. And then we migrated we modified the allocation policy to move data around, and that gave us again better locality, better cacheability, and reduced the number of flash accesses. So if you combine all these different techniques together, right, you get many axes of improvement over the baseline, which just blindly executed those applications on the CXL SSDs. So we think CXL SSDs are a really interesting technology. They significantly improve TCO because flash is just scaling so much better. There's also a nice scaling trajectory for the next 10 years that we can work with. CXL is great because it exposes a byte addressable interface, makes integration of these devices very straightforward. But Flash is slow, and we need to support smart hardware software co-design to address these issues. And software hints, we believe, is a good way to do this. So I want to wrap up with just one shout out. I'm not too familiar where you all from, but if you work in industry and you want to collaborate with us or other academic institutions, please consider doing so now more than ever, because you may have followed the news that academic research is really under attack, and we are struggling with supporting our students and continuing our research. And we have already started scaling down our endeavor in terms of faculty and PhDs. And so I think if you want to continue being able hire excellent educated talent after maybe in the next 5 years or so, then consider supporting us. So it's really important if you want to see research like that to continue. And if you want to talk to your managers, or you find some programs within your company, some calls for research collaborations or whatever that your company may support, please reach out to me, right? I'd be happy to talk with you about how we could collaborate. And this is just an overview of what we can offer. I think this call out was in general, please support academia. Now what we bring to the table is this Center for Research in Systems and Storage, which I already mentioned at the beginning. We have a wide range of research projects, data centers, scalable systems, systems for machine learning, and also how to use machine learning techniques to improve systems performance. We have a lot of projects on CXL going on right now. I think there's 4 PhD students working on CXL-related memory tiering projects. And we also have some work on security and sustainability. So you can check out crss.ucsc.edu if you want to check out what the center does, and you can reach me personally, of course, as well. And yeah, it's the center is supported right now by 5 companies, Intel, ARM, some from the storage space, some from the data center space. And so we have these tight collaborations where we work together on projects that are highly relevant for industry, and we learn from industry what problems and challenges they are facing and they want us to look at. All right, so great. 8 minutes
Thank you,
left. That's
Professor,
all
for
I
the
have.
great talk.
Yeah, thank you
Yeah,
for
we do
the.
have a few questions and also in the chat, and Victor raised his hand. Victor, go ahead.
Yeah, I have a question. So they're thank you for the talk, very interesting. So they are trying to figure out how the two sides talk to each other, right? On the application side, there is some effort doing higher level.
I can no longer hear you. I'm not sure. Is that only me?
From a yeah. So you need to know the application from a higher level. Then also on the hardware side, how to provide the matrix that's also like what level is the best, I guess, when it comes to capturing the matrix as well as the software requirement hints. I don't know. So you mentioned telemetry data. Is that what level is that on? I guess that's the question.
So the telemetry data is gathered in hardware, and what it can do is it can observe, for instance, that particular memory. So It can observe the address ranges, for instance, the pages that cause most of the flash to DRAM data movements. It can measure the memory ranges that trigger the most cache misses. It can observe which data ranges and prefetches are successful and whatnot, right? So what's the prefetching coverage and accuracy and so forth. And it can report that data to the software. Itself, it doesn't know what a memory range or a page refers to, but the software can then map this telemetry data back to software application contexts. So, for instance, it can, we found out, right, using this telemetry data that essentially there was in one of these algorithms, there was a struct, and this struct was per object, and each struct included two types of data structures, a vector and a map. And those, because they were allocated as part of the same struct, they were often shared essentially the same page that they would place their data on. And because of the very different hotness and data access characteristics, that didn't work out well. So what we did is essentially we split the struct into two, and then we had an array of the first half of those structs and another array of the second half of these structs, right? And by doing so, we split these data structures onto different regions in main memory, and that delivered considerable performance improvement. It required some software modifications, but it was like 3 lines of code that we had to change. And this is something you don't figure out yourself, right? You have to have very detailed low-level profiling and telemetry data capturing to even learn that these are issues that need to be addressed on such a system. And they probably have not been an issue when running the same code on just pure local DRAM, but they appear when you run it on these devices. So that's just an example of what you can do there.
Yeah, may I reach out to you for a follow-up question? Because the main problem is higher level application intent versus lower level. Because having lower level hotspot doesn't mean that's a problem sometimes. It's really what the application want to do in a higher level that matters. Yeah. So if you can maybe provide your email, I can then follow up on this. I don't want to, and somebody else may have other questions.
Yes, please reach out. Happy to talk more.
Hey, Professor, I have a question. So you mentioned that you basically using compiler to inject software hints. I'm curious that is their compiler source code based or it's more kind of a binary based compiler?
So this is a pass in LLVM that we wrote. So as long as you are based, or your infrastructure uses Clang, LLVM, I mean, I'm sure you can port the same pass to GCC as well. You can essentially use it. So it needs some profiling to detect basically the loads that suffer from cache misses. It will then perform a data flow analysis, right? It will go into the LLVM IR. It will find the load. It will extract the address computing slice. So it will perform a backwards data dependency analysis to determine all the instructions that are used to compute the memory address based on the application context, like the node and the edge list and all that. And then it will inject automatically a kernel that basically does the same thing. It performs the address computation, but instead of performing the load, it performs a prefetch, and it performs that with a certain distance so that it can look ahead and prefetch future nodes or nodes that are being accessed in the future. And
Okay.
then this new prefetch slice, we call it, is automatically injected into the LLVM IR, and then we recompile, and then it's part of the machine code. And so we did that for memory, but this works also very well for this CXL device. You just essentially add a new slice to compute the right prefetch address, and then you call our hint API to transfer that prefetch address to the CXL device, and it will make sure that the data is corresponding data is prefetched.
Okay, thank you. Hey, Randy, I saw you have a question in the chat, so do you want to ask now?
So the question was about difference between write and read heavy data, right?
Yes.
So yes, absolutely. This is another thing we are looking at. For DRAM, again, it almost doesn't matter whether you're reading or writing. The performance is essentially the same. For Flash, it's a substantial difference. Not only are writes much slower, but as you know, we also need to erase on the block level granularity. And so you cannot do in-place updates. So you need to garbage collect and migrate data around. So writing incorrectly or inefficiently can be a big problem. There's a lot of work already with ZNS and FTP and Open Channel to address this kind of problem on the SSD layer. And these techniques can be made even better and I think more transparent with such a data structure, right? Where you can give these explicit, say, data placement hints to improve such things. And again, you may want to lay out your data structures differently if you know, hey, this is a write-heavy data structure. This is a read-heavy, then you want to make sure that they operate on different memory regions.
Do we have more questions?
Oh, I just want to make sure I got the email I see online. It's HLITZ at UCSC, right?
That's correct, yeah.
Oh, all right, thank you.
All right, great. Yeah, thanks for having me. We are at the hour. Please reach out, right, if you want to do something together. All right.
Thank you very much, Professor.
Thanks. Bye-bye.
Bye.